So in this video, we're going to take a look at the AB Calculus exam from 2010, free response question number 6. In this problem, the main topics that are assessed are tangent line approximations, separable differential equations. Frequently in these type of problems, you're also asked about implicit differentiation or slope fields, but in the 2010 exam, that wasn't the case. But you can prepare yourself for that event. So now in part A, they want to find the equation of a tangent line. So to write an equation of a line, one method is to use point-slope form. So y minus y1 equals m times x minus x1. Since we're given some information about a point, we're told that when x is 1, your y coordinate's 2. And we're given information about the slope. We're told that the slope of the function y at any point in time, dy dx, is a product of the x-coordinate times the cube of the y-coordinate. So plugging in the point 1, 2, we find that our slope at that point of our tangent line is going to be a slope of 8. So go ahead and plug in 8 as our slope. And the point at which we're evaluating this tangent line equation is at the point 1, 2. So I plug in 2 for y1, and I plug in 1 for x1, and I get y minus 2 equals 8 times x minus 1. Now, if you need to write it in function notation, then just say f of x is 8 times x minus 1 plus 2. I just bring the 2 over to the right-hand side by adding it. Part B says, figure out, using this tangent line, what the approximate height of the actual function is at 1.1. So I'm going to plug in 1.1 into my tangent line equation. And I get that the approximate height is a height of 2.8. Now, is this going to be an under or over approximation? Well, that depends upon the concavity. If my function's concave up, my tangent line will lie below the curve, near that point. If my function's concave down, my tangent line near the point of tangency will lie above the curve, so it'll be an over approximation. So, second derivative is what tells us information about the concavity. So I'm going to evaluate the second derivative at the point 1, 2. If we hadn't been given this function, I'd have to take the derivative of dy dx implicitly, and I'd have to figure out what that would be. But luckily in this case, we're actually given that information. So it turns out that the second derivative is positive at the point 1, 2, which means that my function's concave up. Therefore, my tangent line lies below the curve, so therefore it will be an underestimate. I'm going to go about finding the solution to the differential equation. Dy dx equals xy cubed. That goes through the point 1, 2. So I'm going to go ahead and separate my variables, getting my y's with my dy's and my x's with my dx's. I'm going to integrate both sides. So the antiderivative of y to the negative third, we go and add 1 to our exponents. That would give us, we go up a degree, so it'd be y to the negative second times the compensation factor of -1/2. And then technically we have a plus c over on that side, but since we're going to bring all the c's, all the constants over to one side, this big C here represents the combination of both the c from either side, because you have the difference of two constants, it's just the same as another constant. So it'll all end up coming out in the wash. So now what I'll do is I will plug in my data point, the point 1, 2. So the thing we got right there was the general solution. If we want the unique solution, we plug in our data point. So I plug in 2 for y, and I plug in 1 for x, and I'm going to go ahead and solve for my value of c. So therefore that gives me -1/2 times 1/4 equals 1/2 plus c. So then I get -1/8 equals 1/2 plus c. So therefore, C is equal to a value of negative 5/8. Now what I'm going to do is I'm going to isolate y by itself. So I'll plug in my C value and then I will get y by itself. So I have negative 1/2 times 1 over y squared equals 1/2 x squared minus 5/8. Let me go ahead and multiply everything by a negative 1/2. So, sorry, divide both sides by negative 1/2. In other words, multiply both sides by negative 2. And that would give me y, 1 over y squared equals negative x squared plus 5/4. So therefore, y squared is equal to 1 over negative x squared plus 5/4. So y is going to be equal to plus or minus 1 over negative x squared plus 5/4. However, because we're going through the data point 1, 2, we only need the positive square root of that. So now I'm going to go ahead and just give a little visualization here. I'm going to sketch a graph of the slope field for x times y cubed. As we can see here, this is what it looks like. And then I'm going to sketch a graph of what my solution looked like. And there you have it. That's what that function looks like. That goes to the point 1, 2.